Hello everybody. Today we're going to continue our DC and AC analysis, and today is the turn for BJT circuits. We basically going to follow the same pattern and workflow from MOSFET circuits we presented in previous video. So let's get started. Before doing anything else, groundworks must be solid and successfully conducted. 3 identifications: terminals, types, and common circuits. Okay. Since I have introduced these in details in previous video, I won't repeat them again here. So let's directly step into the DC analysis. The DC analysis of BJT circuits. Okay, so first of all, being clear that we have NPN or PNP BJT, we correspondingly have 2 routes to go through. Along the NPN BJT route, we assume first of all the active operation region of the BJT. Okay, this is the amplifier application operation region, so we assume it is the case, and based on the given original circuit, we eliminate the AC source and replace the caps by open circuits to come up with the so-called DC circuit. From this circuit, we go ahead to write equations so that we can calculate the variables we need. And the equations are including the relationship between IC, IB, and IE in terms of the gain beta, and also a voltage, constant voltage between terminal E and the B, 0.7 volts or any other given values. Plus we have 2 KVLs. Like the MOSFET circuit case, 1 kVl is out of the VBE loop, the looping containing the voltage between B and E. Another kVl is out of the top, from the top VCC supply to the bottom VE supply, going through the voltage VCE. So these equations are supposed to be enough for us to find out the voltage or current we want. Of course, before we start to do the calculation, algebra thing, we want to check if the number of equations is same as the number of unknowns, which is the condition to guarantee us to be able to find out the individual unknowns. So from the equations, we got IC and VCE. And from there, we need to check if our previous assumption of active region was correct. Okay, by checking VCE is greater than VCE saturation or not. Okay. Before going any further, let's take a look at the other route, the PNP BJT circuits. Nothing different except the variables here. It's not VBE anymore. It's VEB is VEB, not VCE but VEC. And we are checking if VEC is greater than the VEC saturation. Here I want to emphasize one thing. Both VCE saturation voltage and VEC saturation voltage are small voltage. They're generally speaking available from the data sheet of any particular BJT making very small, and it's not very easy to become the saturation. Okay. So going back to the NPN BJT route, if the VCE is greater than VCE saturation voltage, that means our original assumption of active region was correct. And if so, we're done. In the sense that the IC we got is already ready for our later on small signal analysis. But if VCE is not greater than VC saturation voltage, that means it is not active region. In other words, it is in saturation region. If saturation region is the case, then our VCE is equal to the VCE saturation voltage. And then you need one more KVL loop to find out the corresponding IC value. From the IC, we know we're done with the DC analysis. However, just like in MOSFET circuit, this is saturation region for BJT. So this is not amplifier. This is not amplifier. No AC analysis is needed for finding out the voltage gain. Similarly, along the other route, we have same idea and same procedure, except the variable. Okay, that'll be all for the DC analysis for BJT, covering two types of BJT component. As the term for the AC analysis, so based on the obtained IC value from DC analysis, we calculated first of all the small signal parameters, including the GM, the transconductance, and the output resistance, and so-called small signal resistance here. Okay, based on them, we recalling the type of BJT one more time to come up with two different routes again. So along NPN BJT route, we need to first of all come up with the very basic NPN BJT small signal model. This is the basis. This is the basis. We should not have any trouble or mistake. And meantime, get rid of DC source, and capacitor is replaced by short circuit. And if we are assuming talking about the midband, from them we obtain the AC small signal circuit. Along the other route, the PNP circuit, pretty much the same. And again, I'm using the red color to emphasize the difference between two small signal model of BJT. And you should see a different current direction and different voltage polarity. Okay, let's keep moving from the small signal circuit. Along the NPN route, from the small signal circuit, we come up with equations based on the listed tips or say methods. This should be enough for you to have enough equations to solve the unknowns. First equation is output equation again, trying to express the output voltage in terms of V pi, which is also the VBE, by applying simply the Ohm's law. Second equation is the input side equation, trying to express the source voltage in terms of V pi as well. Here you might need KVL or KCL to link the Vs to Vin, and then from Vin to V pi. The last equation is called V pi equation. It's just like the VGS equation in the MOSFET circuit. It's easy, but very easy to be forgotten. For example, a voltage difference between two transistor terminals, or So based on these equations, you should notice number of equations as one less than that of the unknowns. So you know you are not able to find out the individual unknowns except the input source voltage is given. However, since we are talking about voltage gain, so we don't need to worry about input or output voltage. We're just looking for the gain, which is the ratio between two unknowns, so we can find it. Okay, output voltage over the input voltage. Okay, this is pretty much the AC analysis of NPN BJT circuit. Similar procedure for the PNP route, except again the variables. Alright, so that will be all for today's video, and it covers the DC and AC analysis workflow for BJT transistor circuit. And let me know if you have any comments or questions. Thank you.